Oh, it hurts when he says it. So the first thing I want to be really clear about is this is the easiest version of this problem that there is. So if you're thinking this one's hard, you're wrong. This is the easiest version of the problem. This was the gimme on the test that year. There's always a problem on every year's test that has a gimme, one that is straightforward. Every student should have access to it. What I mean by that is if you've been taught the curriculum and you've done moderately well, most students will be able to access this problem. They'll know where to start and they'll know how to at least get through portion of the problem. I'm not saying they'll get it all right, but I am saying that there's usually a problem that is not difficult to access. The problem we looked at yesterday, that was more difficult to access. It was difficult to figure out where to start. And even when you did start, the beginning of the problem was quite difficult, so it was hard to make progress. So that's the kind of difference. You should expect one of each of those on the actual exam because they're going to try and challenge you, but they do want to make sure that if you know some physics, they can see that. This is that problem. Now, I told you that you didn't have to do anything about question B or question E because I had to do a simple harmonic motion, but don't think there's a lot of points tied up there. Question B was the application of one formula that was on your equation sheet. So if you're in physics last year, you should know that things oscillate for a spring mass with that relationship. There's only two oscillators that are even on the equation sheet. You just look for the one that says period for an oscillator and you've got the answer to question B. And it's plug and chug from there. So there was only about 3 points tied up between B and E. But that doesn't mean that you guys know how to do these problems. So let's take a look at how to do these questions. I do want to say that I would not ask question C the way it's asked. I would ask for you to find out what the maximum speed is, not just figure out when it happens. And like I said, add another block here and make this a collision question. And now you're starting to get into what the real problems are going to look like. A combination of a conservation of momentum and a conservation of energy question. Put the whole thing on an incline so that, it's something like this and it's got friction down this incline. Well, now we're talking. Now we're talking about a physics problem. So when I say that this one is pretty accessible, yeah, this one's very accessible. So let's start with, you said question D. I want to talk about question C, and then I'll talk about question D. And the reason I want to do that is question C doesn't address what I think you should be able to do. So let's talk about question C first. In that, we already talked about the knowledge that to get to the maximum speed, we're talking about finding the place where the net force is 0. Because it's then that the object is no longer accelerating. So it's at that point where we're at the maximum speed. So I don't know where that occurs, but likely, hold on. Likely it occurs, someplace where the spring has begun to be compressed. And the fact that the spring is compressed doesn't mean that it immediately slows down. It just means it doesn't accelerate as much. It's still accelerating downwards. As the force from the spring increases, it'll eventually reach a point where the forces are balanced and it's not accelerating. It passes right through that point though, because the block has inertia. Because it has inertia, it will continue to compress that spring, which is why there'll be a larger upward force than downward force, which is going to start to slow the block down until the block comes to rest. So this intermediate point right here is going to represent the point where the block is at its maximum speed. And I don't really know where that is, but I know I can find it because that happens when Kx equals mg. Well, this is a numbers problem. It gave me all the numbers. So x is going to be equal to mg over k, which is going to be 20 over 200 or 0.1 meters. So they've told me that I will reach the maximum compression when I compress the spring 0.1 meters. Questions about that? All right. Well, if I want to figure out how fast the object's going, the best use scenario from what we've taught so far is to use the work energy theorem, where the net work on the block is going to equal the change in kinetic energy of the block. the block is released from rest and its kinetic energy increases. So call this question C part 2. If I want to figure out how fast it's going, if I look at the total work that acts on the block, or total work done to the block, I should be able to figure out how much the kinetic energy changed. So let's look first at the fact that there's work done by gravity on the block, right? The block traveled a total distance of 0.55 meters downwards. Gravity acted downwards on it. So the work done by gravity is positive, and it's going to equal the downward force, which is 20, times the displacement, which is 0.55. And that's the total work done by gravity. At the same time, there is work done by the spring. The spring does negative work because the force from the spring is upwards, but the spring is pushed downwards. So it's going to be negative work from the spring, and it'll be equal to 1/2 kx squared. The spring is compressed 0.1 meters. This has to equal the change in kinetic energy of the spring. Now, there's something I want you to see here. So I'm going to write this a little different. We know this is also related to the gravitational potential energy. This is also related to the elastic potential energy. And what we're really saying is that if we take the gravitational potential energy and subtract the elastic potential energy, that's going to equal the final kinetic energy minus the initial kinetic energy. This is still the work energy theorem, don't get me wrong. But I'm writing it in this way because I want you to consider that there might be a different way to express this, something we're going to be talking about today. If I move everything to the side of the equation where it is positive, I get gravitational potential energy and initial kinetic energy on the left side, and I get final kinetic energy and elastic potential energy on the right side. If you'll notice, this represents the initial state of the problem, and this represents the final state of the problem. You guys from last year should recognize this as the way we described conservation of energy. That you add up all the forms of energy the object has at the beginning, and you set it equal to the forms of energy it has later. And that these must be equal unless energy was taken from the system. The work energy theorem is a statement of conservation of energy. And it should be very clear for anybody who had physics last year that that's where we're working towards. This problem can be done using conservation of energy or the work energy theorem because they are the same thing. The work energy theorem is more powerful, technically, because it includes all possible forms of work that can be done in the system. Conservation of energy tends to be misused because people don't always think of all the different forms of energy that could be existing from one state to the next. But this is how you would find out how fast the object was going when it reaches that point where it's compressed to spring 0.1 meters. Now, to continue this, to do question D, which was actually asked of me, you take all that away, take this away, and this away, oops, this away. And consider that, yeah, there's probably a place where the box will continue to go where it will eventually come to rest. I don't know where that is. But when it comes to rest, that represents the maximum compression of the spring. Now, that doesn't involve this place where it has a maximum velocity. And it doesn't involve this place where it passes through the equilibrium position. It involves the place where the object's velocity is 0. And although I don't know where that position is, I do know that there will still be work done by gravity, 0.45 plus x. I don't know how much it is, though, because I don't know how far it compresses the spring. But I do know that there will be energy in the spring when I am done. That the work done by the spring is negative, so now the energy is stored there. The difference is the object will be at rest here, so the change in kinetic energy will have to be equal to 0. Right, started from rest, ended at rest, so the change in kinetic energy after all the work is done is 0. So that means that 20 times 0.45 plus x equals 1/2 times 200 times x squared. Now this is a quadratic. You're going to have to find your values for x. And be careful here. One of those values might be negative and one might be positive, and you have to figure out which one is the right one to use. It might not be obvious to you, but we have set downwards to be positive in all of these calculations. So because of that, the positive answer is the correct one. But as we talked about in class, the negative answer has meaning. It's what would happen if the box basically got glued to the spring and represents how far upwards it would go. In fact, that's how you would answer question E. You would figure out the maximum displacement by looking at how far down it compresses the spring and how far up it comes with the spring. The displacement is half of that distance. It will also be the distance from the equilibrium to maximum compression. So you already have the two things you need to answer question E when you finally get to question E. All right, that was the FRQ. Did I cover it completely enough for all of you? All right, I'm glad. You guys at home okay? Excellent, I'm glad. That brings me intense happiness. No, it doesn't. It brings me moderate happiness. All right, I don't want to do what I'm about to talk about here, but this is because I was asked a question at the end of class that I am afraid might be ubiquitous, but the one person who asked at least had the courage to ask it. I have a feeling that there might be other people out there who have the same question. So if they don't, and I misrepresented this, then I'm sorry, but I think it's prudent that I have this conversation with you. And like I said, I don't want to, so I'll try and keep it brief, but if it's like I talked in 6th period, it might not be as brief as I'd like. Somebody was concerned because they don't really know what this means. I want to know why I keep throwing it around in front of you. So we're going to answer that question today. But before I get you into it, look, yesterday was tough. At the end of the day, after you guys all left, I sat and thought about whether I should have done the lesson the way I did it yesterday. Maybe, maybe not. But look, I want to be very clear. I am not waiting until you have the calculus skill to do the calculus we have in this class. Because that means I have to wait to do everything that has calculus in it until April of this year. Or next year, sorry, next year. If I wait till then, that gives us what, 2-3 weeks to do every bit of calculus before the exam? I'm not going to wait. We need to have exposure to this stuff now. Now, maybe I won't test you on it or test you as frequently. And maybe I'm going to cut some corners as to what it is the calculus teachers might want you to know. I trust in the calculus teachers to teach you calculus in its form that you need for their exam. But I need you to have some of this skill earlier, and you're going to have to stop being scared of it. You'll have to acclimate and rise to the challenge. So I don't want to hear that we're not doing that yet. I will ask where you are just so I get an update. But doing it or not, if it's taught in class, I expect you to be able to do it, or at least attempt it. Look, very few of you had difficulty finding the antiderivative in order to find a motion equation. This isn't much different than that. So what we're going to do is something like I said, I don't really want to do, but I think it will help because you've done this before. I've asked you to figure out what the velocity is after giving you an acceleration equation. But now I want to do it formally so that you can understand what the special little, squiggly symbol is. So let's start first by an understanding that this is unlikely to be any question on any exam. It might be more likely where you'll get net force equals MA, and maybe that equals some function. I can believe that. But to be just given an acceleration function like we were yesterday, unlikely. I've seen that on 1 or 2 exams over the course of all 30 years. But they've done it, so that's why you had to see yesterday's. I do want you to realize that you already know how to get the answer here. If I asked you for the velocity function, you should know how to get the antiderivative. But the antiderivative is actually not really a thing. The integral is a thing. The antiderivative is a part of getting the integral done. So we're going to talk about all of the processes. And there's nothing new here. Everything I'm going to say, you've already been told, but I'm just going to be very formal about it. In order to actually get what I am asking for, the velocity as a function of t, the first thing you have to do is you have to create a differential equation. And we've talked about that. You need to find which one of these variables here is in the form of a differential or can be expressed in the form of a differential. And that's not tough because dv dt is the acceleration. And that equals 6t squared. dv dt can be written a lot of different ways. It's written this way because they want it to look like a fraction. They want it to look like the slope. They want to be stating here that this is the function of slopes, as opposed to writing it this way, which is functionally equivalent, but is telling you to take the derivative of v. They mean the same thing, in the same way that I told you at the beginning of the year, that this means the same thing, that this is v as its derivative of t. It's just shorthand. They all mean the same thing. Now, we have usefulness for them in some of the ways we write them because they allow us to see what's happening in a different light. This one allows us to use the fraction as a means of finding the function. And to do so means to split the derivative, which we've talked about. Splitting a derivative merely ensures that I can begin to line up my function in such a way that the variables line up together. Now, I can do the same thing to both sides of an equation. That shouldn't be a surprise. I could raise both of these to the base of e. That shouldn't be a surprise. I am allowed to do functional equivalence to both sides of an equation. I could invert both sides of the equation. That's okay. Taking the derivative of both sides of an equation is okay, and taking the integral of both sides of an equation is okay. That's functionally equivalent. So if I want to get my function by itself, I need to take the integral of both sides of the equation. That means drawing the little symbol. But that's not enough. Drawing the little symbol means I am going to be taking the integral of each side of the equation independently. But the integral symbol is a symbol of a process. It means more than that, and your teacher will be happy to explain all the different nuances of what those are. I'm not going to. But the integral symbol is a way of organizing information in order to do a process. It has 4 parts. The first is that there's the symbol itself, which means the summation. Not because I want the summation, it's because the integral can be calculated by summing the area under a curve. Some incredibly smart person realized that it's mathematically functionally equivalent to find the area under the curve, and it will be equal to actually computing the integral. So that's why the first time this will be introduced, you're going to be breaking up your little curves into lots of little rectangles and adding up the area. Who's already done that once? It's a lot of fun, ain't it? The answer is no, it's not. It is boring. But they're going to do it a lot of times and show you several different methods, right? You're going to get the triangle, the rectangle method, the trapezoid method, the reverse trapezoid method, perhaps. And then eventually they'll say, oh, fine, let's just get the frickin' formula and stop doing that. But they want you to believe that it's the area because they want to support Leibowitz. He was a hard worker as a mathematician. He was no Newton, but he was a hard worker. So they want you to know those things. This gives us a functional equivalent. So that's what the symbol means, to add up, to sum. This is called the integrand. It's the function you're starting with. It's what you're going to find the antiderivative of. For us, it's going to be this. But also, you have this part, the d whatever. This is telling you which variable is the one that's important. Every other variable is a constant, at least in this class. Eventually, you might make it to a point where they're not all constants. And you have to do more functional mathematics, something like partial differential equations. Hard stuff. Never took it. Wasn't smart enough to take it when I was in college. I stopped at just advanced differential equations. But you guys might be smart enough. And the fourth thing are these bad boys right here, these boxes. For us, most of ours are all going to be what are called definite integrals, which means we're going to put boundaries on it. When did this variable start and when does this variable end? A lot of ours feel open-ended, but we are binding them. We are creating what are called boundary conditions. For example, in this problem, we're probably going to say that at time 0, the object had some initial velocity. I'm putting symbols here to indicate where to start my function and where to end my function. The bottom symbols have to be linked together if there's an equal sign. So I have to state the velocity that exists at this time. They have to be linked together. For us, we put in boundary conditions, but we link them together based on reality. This represents how fast it was going at time 0. These aren't hard. We already have definitions for these. What's harder for you guys to understand is that I'm going to put t and v here because there's going to be some time in the future when the object has some velocity v. If you want, you can put vf here so you don't get these confused. But there's 3 of them here. That might be confusing too. I don't care. These are placeholders because at the end, I want a function. I want to relate the velocity of the object at some time in the future with that time in the future. So I need a t there to represent the time in the future. Now, the truth is, at this point, we are doing the right side and the left side independently. After I link the variables, you just have to now do the process of finding the integral. And doing the process of finding the integral isn't a whole lot. It's taking whatever the integrand is and finding its antiderivative, finding a function that existed before. Sometimes that's stupid easy. Yesterday was not hard. We had what, sine? We had to get minus cosine. That was not hard. Today, not so hard. We've done polynomials. You know that I take t and add 1 to it. And then I take my new exponent and I put it in the denominator. There, I have found the antiderivative. Now, I'm not done. That's not taking the integral. That's just a part of taking the integral. I still have to apply my boundary conditions to this. I haven't done that yet. I will, but I haven't done that yet. Why? Because I have to find the integral of the other side too. Now, the other side doesn't appear to have a function, but that's a lie. There's an implied function, 1. It's a constant. But I can't express it in terms of 1. I have to express it in terms of v. So I put v to the 0 power. Again, this is not new. We've talked about this. But I'm treating it like it's new for you guys. What do? I increase the exponent by 1. I take my new exponent and divide the coefficient by my new exponent. I have now taken the antiderivative of that side. I'm not done. I haven't applied my boundary conditions, but I've taken the antiderivative. So now, to finish, I have to apply my boundary conditions, which means putting in the final boundary and subtracting the initial boundary. So the left side's pretty easy. It's going to be putting in V for V, and then subtracting, putting in V naught for V. On the right side, a little more complicated. It's putting in T for T, so 2T cubed, and then putting in 0 for T, minus 2 times 0 cubed. Now, to finish, you're supposed to solve for your functional variable. I wanted V as a function of T. So I'm going to solve for my functional variable. V equals 2T cubed plus V naught. I cannot be more explicit than those things. What's the symbol do? Well, in the basic terms, it gives me a place to hang all my stuff. That's what the symbol gives me. It gives me places to write all the things. Does it mean something? Sure. And for that, break out Wikipedia. I'm sure there's page upon page of information about what that little symbol means. And I really don't care. I mean, it's neat, I guess. Fun if you care about that kind of stuff. Maybe if I was in Mu Alpha Theta and was as smart as those guys, I would care more. But I probably wouldn't make the cut. So let me be a little bit blunt, though. We sometimes have functions that are just expressed as an integral, and there's not a whole lot we can do about them. We created the integral in the last example because we knew that one of our variables was based on a differential. But sometimes we just have functions that have the integral in it. If you want, we could express this as a derivative first if it makes you feel better. You should be able to see that that would have to be functionally the same thing from what we just did. But I don't believe there's as much usefulness for this. There might be next semester when we talk about gravity, but not right now. I do want you, though, even with your limited skill set, to understand that when you're faced with a function that has a derivative as part of its calculation, that what it's telling you to do is to look closely at your problem. Does one of these change as x changes? If it does, you're going to have to do calculus. If it doesn't, you're fine. You don't have to do any calculus. And although you might be asking, well, how do you know? You know. If my block has to be moved to the right, will the force stay the same the whole time I'm moving it, or the force change as I'm moving it? I think you know the answer because we talked about the fact that it's going to take more and more force as I move to the right. That suggests I have to use calculus. I have a function that describes how much force it takes as x increases. So calculus will be required here. That's when I know. And that's not the only time. They could tell me all sorts of different things like this. For example, I put this on the AP Physics 1 test just this last couple of weeks. Let's see. I need those things, and I need one of these. No, not one of those. I need one of these. And I need some of this stuff. And let's see. There we go. So what if I have a guy standing right here and he applies a constant tension to the string? Will the box move to the right? I think it will. It's going to go that way, sure. He can apply a constant tension the whole time. And that'll make the force constant as the box moves to the right. But wouldn't you all agree that theta is not going to be constant as the box moves to the right? That angle is going to increase as the box goes to the right? If the angle increases as the box goes to the right, I'm pretty sure that means I'm going to have to do calculus. Now, I don't know what I would do here. I'm not telling you I have the answer. I'm saying that you need cosine theta as a function of x. I don't have cosine theta as a function of x. It's probably going to involve some Pythagorean theorem and some maybe knowing this height and stuff like that. There might be some funky stuff we can do to figure out cosine as a function of x. Things like knowing that x and this is going to be x plus h squared. I mean, I know there's things we know. We can figure out triangle stuff. So there are ways to express the cosine in terms of x. And I'm only doing this because there are people in the room who we've done this before. So there it is. This is cosine theta in terms of x, the adjacent side divided by the hypotenuse, written in terms of x. I'd put that up there and then I would do my work calculation, although I don't really know what the integral of this or what the antiderivative of this is. That would make that hard. So I don't want to do this, but I'm telling you it's not so terrible. All I'm saying to you is that you should be asking yourself if either of these things changes. If it changes as the object moves in x, it means you're going to have to do calculus. If it doesn't, it means good old-fashioned algebra, here you come. All right? There. Very, 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 I hope, detailed enough where I don't have to answer those questions anymore. And I don't want you to be scared. Are we going to have to do calculus on the exam? Yes. If you want a 5, you will have to do calculus on the exam. So we're not going to be scared of it, but we are going to have to learn how to do it. So today, we have time left. I want to talk about conservation rules, specifically conservation of energy, but generally conservation rules. You guys have already learned conservation rules. So there's not a whole lot that I want to add to what conservation means. I mean, it means to stay the same. That doesn't tell you very much, but it's a start. You guys have already learned that this is not true, right? Why is this not true? Thank you. It's not balanced. You guys had chemistry, so you should be able to balance this. Do so. Tell me what I have to do to bring this into harmony with the universe. Only 2 of you? That's really bothersome, everybody, because you passed chemistry. So no, put your hands down. But when I ask a question where everybody better know the answer, every hand better go up. I don't care how scared you are being called on. Just show me that you remember something from, last year. Yeah, we all know this. It was physical science in the 8th or 7th grade. Yeah. Now, I hope you understand this is a conservation rule. If I have 4 hydrogens on one side, I have to have 4 hydrogens on the other. The number and type of atoms has to stay the same. It's a conservation rule. So for every chemical equation, balancing is obeying conservation rules, because we know the number of types of atoms don't change during chemical reactions. Now, that being said, all conservation rules are like that. They state that the quantity of something doesn't change over the course of your observation. There are lots of conservation rules in nature, And they're powerful rules in that they help us understand how the state of a problem changes. We're going to study conservation of energy. But the truth is, conservation of energy is a universal idea to which that doesn't tell us anything. In fact, the truth is, I'm supposed to tell you that energy is always conserved. But if I want to be honest with you, I have to say that there's always a conservation of energy and or mass, because that's truthfully what's happening in the universe. Mass is being converted to energy and back, but the total amount of mass and energy in the universe is constant. Of course, if you start talking to some of these really fancy physicists now, they might begin to disagree with that statement, because things are getting a little funky in the old astrophysicist departments now. We are going to be very careful, though. We're going to talk about conservation of mechanical energy. And this is far more specific. Conservation of mechanical energy states that in a system in which only mechanical forms of energy exist, the total mechanical energy remains constant. Now, I know that doesn't say what you probably are hoping for, but what it really means is if there's no force taking energy away into a non-useful form, then we get a one-for-one reciprocation of energy. If there's nothing to take energy away into a non-useful form, then we get a one-for-one reciprocation of energy. Non-useful forms, heat. That's the non-useful forms. So basically, as long as there's no kinetic friction, we have three forms of mechanical energy. There's elastic potential energy, sometimes called spring energy. There's gravitational potential, and there's kinetic. These are the only three forms of mechanical energy we have. If there's no kinetic friction, then we can get a one-for-one exchange for energy into any or all of these three forms. Meaning our energy can flow between these three forms and we don't lose anything. If I add 3 joules of elastic potential energy, I can get back 3 joules of energy and apply it wherever I want. Meaning this sum remains constant for all states of our problem. This is an ideal situation. It's not a real situation. Real situations, although conserve energy, they tend to have things where the energy can't be gotten back in a one-for-one manner. For example, work done by kinetic friction. Once work is done by kinetic friction, it's gone. I'm not getting it back into kinetic energy. Work done by air resistance. Once it's gone, I'm not getting that back. It's hard to get it out of the air molecules. Those things take the energy and convert it into a form that's not easily accessible. And although there might be a way to get that energy converted back, it's never going to be one-for-one. You can't convert heat directly into motion, not in a one-for-one way. You're going to lose something. There's only so much energy you can extract from a heat system. So let's talk about how this actually plays out in our problems. And this is where we really start to get functionally important. So I'm going to make the most obvious starting problem that there is. And it's, you know, one of these loop-de-loop roller coaster questions. So let's have that. Let's have this. Let's be patient with the time. So consider a toy car that is pressed up against a spring, where I can release the spring and shoot the car. So I pull back the car against the spring and release the car. And the car can travel through maybe several different places on the track. So I got A, B, C, D, E, F, G, H. If I say that this is an ideal system, or one in which there is no losses due to kinetic friction, then once I give the spring energy, the total energy of the system remains the same for every state of the problem. Now, there's infinite number of states here, but I chose 8 different states: A, B, C, D, E, F, G, and H. Those are 8 different states of the problem. Each one of them represents a different place where the object is, but all of them have the same amount of total mechanical energy. When I look at these various states, I represent that the object started with some elastic potential energy in the spring. When it was released, it gave that energy to the car in the form of kinetic energy. I'm noticing the height of the car didn't change between state B and C, which means the car still likely retains kinetic energy at C. The height's beginning to change, which means I'm going to have some gravitational potential energy, but I must have kinetic energy if the car makes it to E. I know that the car must have gravitational potential energy and kinetic energy at E, or else it can't be traveling in a circle. Has to have some velocity. Has a gravitational potential here because it's above the ground. Has some kinetic too. Makes it back to C. Looks like it's going to have gravitational here at G, but it's going to have kinetic too. It is possible that H, all it have is gravitational potential. But what it tells me too is that I can set any 2 states equal to each other. I can set them equal and analyze the amount of energy that exists. That's what conservation of energy is about. And with that, I'll say good afternoon, have a wonderful day, because as the person outside clearly indicated, it is time for you to go. 3:35. Boy, has that been fun. So you guys at home have a fantastic day. Tomorrow we'll dive into this a little bit deeper. Also, you should have your homework done by tomorrow. And that's about it. So see you all on the flip side. Bye-bye. Bye-bye, folks at home. Bye-bye, folks at class.